Have you ever wanted to build an argument that's just so solid it's unbreakable? Well, today, we're not just going to talk about it, we're going to grab the actual blueprints. We're going to break down the architecture of logic, piece by piece, so you can build reasoning that really stands up to anything.
So how do you build an argument that can't be broken? Look, it's not about being the loudest person in the room, it's about having the strongest structure. And just like any good building, it all starts with the foundation.
You know, every great piece of architecture, whether it's a massive skyscraper or a tight logical proof, it starts with one single solid building block. And in the world of logic, that block is a statement that is clearly, verifiably, either true or false. No gray area.
We call this fundamental building block an assertion, or sometimes a proposition. It's basically just a sentence that makes a claim. The absolute key here is that it has to have a definitive truth value. It can't be a question, it can't be an opinion. It's either true or it's false. That's the one and only rule.
Okay, let's look at an example. The statement on the left that if you square any real number, you get a result that's 0 or more, that's just unshakably true. But the one on the right? That's definitively false. The thing is, both of them are perfect assertions because they have a clear true or false status. This is the bedrock, the solid ground we're going to build everything on.
So we've got our building blocks. But a pile of blocks isn't a building, right? We need tools to actually connect our assertions. These are our logical connectors. Think of them as the mortar that lets us join simple statements together to form really sophisticated arguments.
Let's start with the three most basic tools in our toolbox: not, and or. Not is super simple. It just flips the truth. If it's raining is true, then it is not raining is false. Easy. And needs both parts to be true for the whole thing to be true. While or is a little more relaxed. It's true if just one of the parts is true, or even if both are. Simple, right? But incredibly powerful.
All right, next up is the big one, the if-then statement. We call this an implication. This is the real engine of deduction. It's how we build a chain of logic. The rule is simple, but it's so important. An if-then statement is only, and I mean only, false if the if part is true, but the then part doesn't follow through. In every other scenario, the logical link holds strong.
And this just shows you how central this whole if-then idea is to our language. P is a sufficient condition for Q, or Q is a necessary condition for P. These are all just different ways of dressing up the same exact idea. If P, then Q. Learning to spot this pattern is a game changer for breaking down arguments you hear every single day.
So far, we've been dealing with individual statements. But what if we want to make a claim about a whole group of things? How do we set the scale of our argument to talk about some things, or even all things? Well, that's where quantifiers come in.
We really have two main types. The universal quantifier, that's the upside-down A, it means for all, or for every. It makes a big, sweeping claim about every single member of a group. Then you have the existential quantifier, the backwards E. It's a lot more modest. It just claims that there exists at least one member that has a certain property.
This seems pretty straightforward, but it leads to a really crucial question. Does the order of these things actually matter? And the answer is absolutely 100% yes. Getting it wrong can completely shatter your logic.
Okay, take a look at this statement. It reads, for all non-negative numbers x, there exists a non-negative number y such that y cubed equals x. And yeah, that's totally true. Pick any non-negative number you can think of. It has a cube root, no problem.
But watch what happens when we just flip the order. Now it says there exists a single number y that is the cube root for all other numbers x. That's completely false. It's absurd to think there's one magic number that's the cube root of everything. So the lesson here is critical. With quantifiers, order is everything.
So we've got our blocks, we've got our connectors, and we've got our quantifiers. Now, how do we actually assemble them into something that holds up? Well, we use proven methods of reasoning. You can think of them as the architectural blueprints for building a valid argument or a proof.
First up is a method called analysis synthesis. This one is great for solving problems. Think of it like being a detective. In the analysis phase, you work backwards, you look at the evidence, and you figure out all the possible suspects who could have done it. Then, in the synthesis phase, you go through your list of suspects and you test their alibis to see who the actual culprit is.
Proof by induction is kind of like setting up a massive line of dominoes. First, you have to prove that your statement is true for the very first case. That's like knocking over the first domino. Then, you prove that if any given domino falls, it's guaranteed to knock over the next one in line. Once you've done both of those things, you've proven it's true for all of them, forever.
And of course, there are a bunch of other blueprints in the logical toolkit. You can just argue directly. Or you can use clever techniques, like the contrapositive. A really powerful one is proof by contradiction, where you assume the opposite of what you want to prove and show that it leads to something totally impossible. Or you can just break a big problem down into smaller, manageable cases and solve each one.
Now, I know you might be thinking, this all sounds really abstract and mathematical. But the beautiful thing is, these exact same blueprints are being used constantly to build arguments in the real world, whether we even realize it or not.
Just think about it for a second. When a lawyer in a courtroom proves an alibi is impossible, that's a proof by contradiction. When an IT specialist runs through a checklist to figure out why your computer isn't working, is it the power, the cable, the software? That's a disjunction of cases. When a business analyst projects future profits based on current data, that's direct reasoning. These structures are everywhere. They're the invisible architecture of clear thinking.
So what we've seen is that logic isn't some abstract art form. It's an architecture. It has a foundation, it has tools, and it has blueprints that anyone can learn to use to think more clearly and argue more effectively. So the real question is, now that you have the toolkit, what are you going to build with it?